Hi everybody, in this video you're going to learn about quadratic systems. We're going to take a look at quadratic linear systems, quadratic-quadratic systems, and situations that can be modeled by a quadratic linear systems. We're going to use Desmos to solve these problems. So here on our first problem, our first piece of information, we have a graphic here. And in this graphic, it provides us with a quadratic function and a linear function. We know it's a quadratic because it is squared. We know that it's linear because it's a linear term and there is no exponent on there. So that means that exponent is 1. Therefore, this function is a linear function and this is a quadratic function. So it is possible to have two solutions, meaning that when the two equations are graphed, right, there are two instances where the functions will actually be equal to each other. That is what you call a system. When you graph two or more functions and you look for the intersection, you look for when they're going to be the same. So it's possible to have two solutions. In this situation, it's possible to have one. And in this situation, there are no solutions. So let's go ahead and graph this out so that you can see it here. We have a quadratic. We can turn this on so that we can see the quadratic there. Now, if I want to see where it has two solutions, there goes the two solutions. Desmos allows us to click on the intersection and it will give us our answer. So if I click on the intersection here, I can see that my solution, my point of intersection, is negative 2.303, 1.697. My second solution is 1.303, 5.303. So that is a situation where we have two solutions. Now let's look at the situation where we only have one solution. So here, our quadratic and linear function is intersecting in one location. If you click on it, again with Desmos, it tells you that the answer is negative 0.5 and 0.25. That is the point of intersection. And it's only intersecting in one place. Now let's look at the last situation. In this situation, we can see that the two functions are not intersecting at all. At no point will these two functions ever, ever, ever be the same. For this example, we're going to look at quadratic-quadratic systems. In this situation, we're going to have two quadratics being graphed on the same graph. So let's look at the first, and again, just like before, we have a possibility of having two solutions, one solution, or no solution. So here we have actually the quadratic graphed in intercept form, and the second one is graphed in vertex form. So these two graphs are actually intersecting in two locations. Again, Desmos allows us to click on the intersections to see the answers. So my first solution is negative 1, 5 for the system. And my second solution is 1.25, 1.063. That is the second solution or the second point of intersection. Now, let's look at the situation where there's only one solution. So this is graphed in vertex form, and so is this. And when they intersect, they only intersect in one place. And that one place is 0.225. That is the point of intersection there. All right, now let's look at the last situation of no solution. That means there is no point where the graph is actually going to be equal to each other. So when looking at this visual, you see that they never, ever, ever intersect. Therefore, there is no solution. So now we're going to take a look at situations that can be modeled with a quadratic linear system. So a classic physics problem states that if a projectile is shot vertically up into the air with an initial velocity of 139 feet per second from an initial height of 101 feet off the ground, then the height of the projectile, h in feet, t seconds after it is shot, given by the equation, h is equal to negative 16t squared plus 139t plus 101. So we have only one question here, and that one question is, find the 2 points in time when the object is 136 feet off the ground. Round your answer to the nearest hundredths of a second to decimal places. So let's answer the question. The answer is the object is 136 feet off the ground at the following times. And we're going to separate those answers by a comma. So I want to know when this function is going to be equal to 136. 136 is the height above the ground. H stands for height. When is this function going to be equal to 136? So what we do here is we go ahead and graph the function y equals negative 16 x and then square it plus 139 x plus 101. All right, so with this graph, I am able to see both the width of the parabola, okay? What I can't see is the height of the parabola. And I already know I need to go high because I need to figure out what 136 feet is. And here I am at 4, right? So I need to adjust my visible range to accommodate the 136. So I'm going to change it to say 150. Okay, that's what I'm going to do. And now I'm going to graph y equals, because that's the height, 136. And voila, I can see where this line, 136, is intersecting the parabola. It's actually intersecting in 2 places like the problem said it would. So my first time is 0.26 seconds, and my second time is 8.428 seconds. Remember, when recording your answers, you're going to separate it by a comma. You're also going to round it to 2 decimal places. So 0.26 and 8.428. 28 actually rounds to 43. So 0.26 and 8.43. Onward to the next example. A person's systolic blood pressure, which is measured in millimeters of mercury, depends on a person's age in years. The equation P, which again stands for the blood pressure, is equal to 0.007 y squared minus 0.01 y plus 120, where y stands for the number of years. So this function gives a person's blood pressure P at age y years. So there's 2 questions we need to answer. Question number 1, find the systolic pressure to the nearest tenth of a millimeter for a person of age 42. In the next problem, we're going to look at if a person's systolic pressure is 133.73 millimeters, what is their age rounded to the nearest whole number? All right, so this problem can also be solved by a system for part B. But for part A, so let's look at what they gave us. They gave us 42 years. Well, 42 years stands for Y. Remember, Desmos is not going to recognize P. So I need to change the P and the Y values. And I need to change them to Y and X respectively. So our function is going to be Y equals 0.007 X squared. Okay? Minus 0.01 X plus 120. All right, so I can't see my graph. Remember, my y-intercept is 120, and here I'm at 4. I definitely cannot see my graph, okay? But I actually don't need to see my graph in order to answer this particular question, which is find the systolic pressure to the nearest tenth of a millimeter for a person of age 42. What you need is the function, and age 42 is our x coordinate. So everywhere we see an x, we are going to type in, we're going to type in 42 to find our answer, to find our blood pressure. And as you can see, our answer is 131.928. Like we did before, we can also find an answer by looking at the table. Okay, so I have the function here. I'm going to go to the gear. I'm going to type in the table here, choose a table, and then I'm going to type the number 42 in. And as you can see, it gives us the answer 131.928. All right. Now, I need to adjust my window so I can see everything. So let's go ahead and do that. So go to your wrench. Let's go take a look at the function. So our function, again, I'm at 5. My y-intercept is 120. I need to change my y values to a number that's bigger than 120. So I'm going to change it to 200. I'm in the range, but it's kind of flat. I can't really see it, right? So I'm going to change my x values to accommodate the flatness of this graph. So I'm going to widen my domain to 200. Ooh, look at that. And let me do it on the other side so I can see both sides of the graph. So negative 200. And there we go. So now we can see the parabola pretty well. Okay, so the question was, when is it going to be 42? Well, unlike before, right, it's going to be hard to kind of tell what is 42 on here, right? 20, 40. So this is actually, because this right here goes to 50. So 42 is going to be somewhere in here. And I can come to the graph and look for 42 as best as I can, right? But who has time for that? That's why it's easier for you to just plug it in or use the table. Now, the second part of the question asks if a person's systolic pressure is 133.73 millimeters, right? So I want to find out when is this function going to be equal to 133.73 millimeters. So I'm going to go to y equals, and I'm going to type in 133.73. Voila, there goes the intersection of this quadratic linear system. So it actually is equal to it twice, right? And if a person's systolic pressure is 133.73 millimeters, what is their age rounded to the nearest whole number? So if I click here, they said X stands for age. Is it possible for somebody to be negative 43 years old? Nope, so that's not the answer. All right, so our answer is actually going to be here at 45 years old. They said round to the nearest whole number. So our answer is 45 years old. So you are going to type in the following answer. 45 here and 131 point, they said 928.